you already know about Math 9, that wonderful feature of a calculator that did not exist when I was in high school and college, but you guys have the advantage of having that Math 9 feature. But what is the calculator doing when it's doing Math 9? How does it figure it out? How does it know what the answer is? That's what we're going to talk about today. So what we know about Math 9 so far is we know that Math 9 has us putting in bounds of a and b into an integral. It also asks us to tell us what the function was, and it needs to know what the axis is. So that's how that Math 9 works. What the calculator is doing is it is able, with its programming features, to figure out the antiderivative of that. And so in its inner workings, the calculator determines what the antiderivative of the integral is. So it's doing all of that instantaneously. It also is smart enough to know that there has to be a c value on there. So that's what it does with the function. That's why it needs to know a function, so that it can figure out what the f of x is. But then what does it do with the bounds? The way we write that on paper is that we end the antiderivative with a bracket, and we put the bounds a and b. And so it's still a way to keep the bounds there, but to show that we've done the process of the antiderivative. So the integral is the name of the symbol. The antiderivative is the process by which you figure that out. Then what does the calculator do with the b and the a? So what it does is it takes the top number first, and it plugs it into the antiderivative. And it evaluates what that number will come out to be, plus the constant c. So it does that first. Okay, so say you put in, 50 as your top number. Well, it'll take the number 50 and it'll plug it in. Minus, it will do the same thing with the lower bound. It will take the a and it will plug it into the antiderivative, also with the plus c. And it subtracts those two values. And then it finally will give you the value of the exact area. So you already know that the calculator can do it. Now you just need to know how it's doing it. Okay, it's not showing you all of the little inside stuff it's doing, but it does that instantaneously and gives you an answer. So the next step in your learning of calculus is for us to take the calculators away and have you do that yourself. Okay, we don't give you massively complex functions. We give you pretty straightforward functions for you to figure out the antiderivative for. We do save the really hard functions for the calculator. That's why you guys as students are asked way harder questions than I was ever asked as a student, because I never had a calculator that could do it for me. And so, yes, you are going to be asked some really hard questions, very complex functions, but the calculator then will do that part for you. Okay, so let's practice the simple kinds like I used to do that you don't need a calculator for. So, for example, you might be asked to evaluate negative 3 to 1 of the function x squared dx. Now you could get close to the right answer using RAM or TRAP or SIMP, because what this is doing is finding the area under a parabola that's a little better. Okay, from negative 3 to positive 1 and above the x-axis. So last week we were finding this, we were estimating this with different ways. We were estimating it with either rams or a bunch of trapezoids or a bunch of Simpson's paraboloids. The only way we could get the exact answer was to have the calculator do it for us. Well, now you're going to learn how to do the exact answer yourself. And so what we're going to do is we're going to find the antiderivative of x squared. And so we're going to raise our power on x squared to an x cubed and divide by the new value of that power. And we're going to add the constant c And we're going to go from the starting value of -1 to the top value of +1. And then we plug in, and we always start with the top number first. And so in parentheses, we're going to plug in the top number of 1 into that function. So it'll be 1 cubed over 3 plus c. And then minus, and then you plug in the second value, what we call the lower bound. So that will be -3 cubed over 3, also plus c. So that gives me 1/3 plus c in the first set of parentheses. It gives me -27 over 3 plus c in the second parentheses. And then I distribute that negative. So I'll have 1/3 plus c plus 27 over 3, which reduces to 9, and then minus c. So what happens to the c's? They do. They cancel out because you have a plus c and a minus c, and those will cancel each other out, and so you're left with 1/3 plus 9, which is 9 1/3, or 28/3, which is the exact area trapped under that parabola above the x-axis between the bounds of -3 and 1. That's what the evaluation of the calculator is doing when it gives you the exact answer. RAM and simp and trap will get you close, but they'll either always be an overestimate or an underestimate, depending on whether it's decreasing or concave, or depending on what method you're doing. Okay, so it's pretty fascinating that that's what the calculator is doing and how quickly it can do it. So let's try another one. All right, we're going to evaluate the integral that goes from -1 to 1, and this time the function is a 4th degree function. Those look like W's, so 2x to the 4th minus 4x squared plus 2, and again we're going to be above the x-axis. Okay, so that function is a symmetric quartic function, and it looks like this. Comes down, hits the x-axis, bounces off, hits the y-axis, comes back down, and bounces off. So it makes sort of this W type of shape. Our bounds are going from -1 to 1, which happen to be exactly where this function hits the x-axis. So what we are looking for is the value of the area trapped below that quartic function but above the x-axis. So as long as you understand what you're looking for, then you're going to do the mathematics on it. And so this will be equal to, now you go through the process of doing the antiderivative. So 2x to the 4th, that's a constant 2, so it'll be 2x raised up to the 5th power and divided by 5. Minus 4x squared becomes 4x, and its new power is cubed, divided by 3. The constant 2 becomes the expression 2x, and then we have c as our constant, which is added to every antiderivative. And we'll be evaluating that from a lower bound of -1 to an upper bound of +1. And now you just drop the values in. So you start with the upper value. And so when we plug 1 in, we're going to get 2/5 minus, and then we plug 1 in again, we get 4/3, plus, put 1 in again, we get 2, and then plus c. So 2/5 minus 4/3 plus 2 plus c, minus the lower bound plugged in. So when I put the lower bound in, I'm going to get -2/5. I'm going to get positive 4/3. I'm going to get -2, and I still have a plus c. Distribute your negative to everything behind, and we're going to end up with 2/5 minus 4/3 plus 2 plus c plus another 2/5 minus another 4/3 plus another 2 minus a c. So nothing cancels here except the c's again. So you're going to have a positive c from the front end and a negative c from the back end. So you add up the common terms. So you have 2/5 and another 2/5, which is 4/5, and a negative 4/3 and another negative 4/3, so negative 8/3, and then 2 and 2 is 4. So you'll want to get a common denominator to add all of that together, which would be 15. So we'll have 12 over 15 minus 40 over 15 plus 60 over 15. So 12 minus 40 plus 60 that's 12/15 plus 20/15 if you combine the negative 40 and the 60 together. So 32/15 is the value of the exact area under that. Yeah.
Like you said, if it's symmetrical, you can just find it.
Okay, very nice, good question. All right, so Jerry's wondering about the symmetry of this graph. Could you just find half of the area and then double it? And the answer is yes. If you were going to show your work on that, what would your, let's do half area. What would the bounds on that be if you wanted to set that up? Say it again?
1 at the top. 0.
Okay, 0 to 1, which would be half of it, and then you'd have of the same 2x to the 4th minus, what was it, 4x squared minus plus 2 dx. And then what would you need to put in front of that to make sure? You'd have to double the value at the end, and that would totally be fine. Absolutely, that would work perfectly well. And that works if you have a symmetric interval. Okay, any other questions? Okay, all right, let's try a third value. Okay, let's evaluate the integral from 4 to 7 of the function 1 over x minus 2 dx. I would expect you to know that graph without a calculator. Okay, 1 over functions that are powers of 1 are always hyperbolas. So if you think about what you know about hyperbolas, these are what normal hyperbolas look like. Okay, that would be a hyperbola . 1 over x. This is 1 over x minus 2, and the minus 2 slides the whole graph to where the asymptote is at the number 2 instead of along the y-axis instead. And so this whole graph now is going to slide over, whoa, that looks funny, slide over 2 units like this, and then the asymptote is coming down through there. I would expect you to have a decent idea, a working knowledge of how to sketch that. Okay, it's just a hyperbola that's been shifted over. And we're going from 4 to 7. And so that's on the right side of the asymptote, because remember the asymptote is at the number 2. And so if we zoom in here, if that's where the number 2 is, then 4 is here, 5, 6, 7. So we're looking at a small amount of area between the values of 4 and 7. Okay, so that's what we're looking for. All right, we're going to do that with the method of antiderivative. Okay. What is the antiderivative of 1 over x minus 2? It's an ln. Okay, now one thing to watch out for, what if it was 1 over x squared minus 2? That's not an ln anymore. So sometimes it's a little dangerous to think, oh, every time I see a 1 over, it's going to be an ln. It's not. It's only if it's 1 over a single power of x, okay, so x to a linear term. So this is for sure an ln. All right, so we're going to have parentheses, ln, absolute value. It's going to be important that you remember those. X minus 2 plus the constant c evaluated from 4 to 7. So when we substitute, we'll have the natural log of the absolute value of 7 minus 2 plus c minus the natural log of the absolute value of 4 minus 2 plus c with parentheses. Now ultimately I don't need the absolute values here because 7 minus 2 is a positive number and so is 4 minus 2. So I'm going to have the natural log of 5 plus c minus the natural log of 2 plus c. If you would ever have a negative number come up with those absolute values, you'd have to make sure to convert it to positive. And then we'll distribute the negative sign. And so once again, because we distribute the negative sign, the c's will end up canceling out. And we end up with the natural log of 5 minus the natural log of 2, which is a logarithmic property, which is the natural log of 5 over 2. The subtraction, the difference of two natural logs, is the quotient, is the natural log of those as a fraction. Similarly, if you would end up with an addition, natural log of 5 plus natural log of 2, that's the multiplication, so you'd end up with ln of 10. All right, how are we doing? Any questions on those? All right, this is going to be the last one of the recognizable integrals. All right, this integral, we're going to go from the number 2 to the number 2 over rad 3. Now, I don't want you to worry about having an ugly bound like that. Usually they are chosen specifically. So that bound, although it might look awkward to you right now, is chosen with intentionality, is chosen with purpose. It's because 2 over rad 3, when you plug it into whatever your antiderivative is going to be, is going to work out nicely. Okay, you're not going to be asked to do awkward bounds. Your bounds will all work out well. The awkward ones are going to be saved for when you do use Math 9. So this is 1 over absolute value x square root x squared minus 1. That one is should be recognizable right away to you as one of our inverse trig derivatives. So its antiderivative will be one of the inverse trig functions. Which inverse trig function is it? All right, this is secant. If it would have been negative, then it would have been negative cosecant. But this is secant inverse of x plus the constant c from the bounds of 2 to 2 over rad 3. All right, now we're going to evaluate this. So we're going to have the inverse secant of the upper bound, which is 2 over rad 3, plus c, minus secant inverse of the number 2, also plus c. Now when it comes to evaluating inverse trig functions, I would encourage you to stick with the main three, which are sine, cosine, and tangent, rather than secant, cosecant, and cotangent inverse. So what I would encourage you to do is switch this problem to be a cosine inverse problem. I think you might find that easier, which you're allowed to do as long as you take the reciprocal of the inside. So secant of 2 over rad 3 is the same as cosine of rad 3 over 2. And again, you can see why it was chosen with purpose and intentionality, because that is a nice number in the world of trig, plus the constant c, minus, and we'll do the same thing here. We'll change it to cosine inverse, and instead of using the number 2, we'll use the number 1/2, plus c. All right, so now we're ready to distribute. So we've got the cosine inverse of rad 3 over 2 plus a positive c minus the cosine inverse of half minus the c. So those c's will cancel out. And then this is where, again, you'll need to have a working knowledge of what values work on the unit circle for cosine, and you'll need to have the radian, the pi measure of where cosine is equal to rad 3 over 2. And so this is 1/6 pi, or pi over 6, minus, and then the cosine inverse of 1/2 is going to be pi over 3. And so the common denominators there would be pi over 6 minus 2 pi over 6. And you end up with negative 1/6 pi, or negative pi over 6. Now, because this answer is negative, what does that tell you about the exact area? It's below the x-axis, or at least most of it is below the x-axis. Part of it could have been above, and part of it could have been below, but a majority of it is below the x-axis on these two bounds. Okay, any questions so far before we move into integrals you don't necessarily recognize? Okay, then we'll do two more of ones that don't necessarily perfectly match something. All right, let's go from negative 2 to 2 of the function x plus 1 to the third. So this is a cubic function. Cubics are those snake-shaped graphs. Plus 1 means it's moved 1 to the left. And so this graph looks like this. And we are going from negative 2 to positive 2. This one hits the x-axis at 1, which means negative 2 is going to be partially negative answers, 0, 1, and 2. So my area is going to be partially negative, partially positive, and then all the way out to the number 2. Now, I'll let you in on a little trick here. There is some symmetry in this graph. All right, the symmetry is between this region and that region. Okay, these two, although are perfectly symmetrical to each other. And if one is below the x-axis and the other is above, and they're perfectly symmetrical, what's going to happen? They cancel out. So, if you happen to notice that, you can go back to your original function, and you can change the bounds. Say, well, I don't really need the negative 2, the 1, or that 0 section. I can start and go from 0 to 2, because that's all the area that's left. It won't be wrong. You will get the same answer if you go from negative 2 to positive 2. So don't worry about if you happen to miss it, but it just might make it easier for you in the long run if you notice that. All right, now to take the antiderivative of this quantity, you can't just raise the 3 power. That only works if it's just plain x. It doesn't work on x plus 1. And so you're going to have to take the x plus 1 and FOIL it out and come up with this expanded form in order to do the antiderivative of each piece. And so this would be x plus 1 times another x plus 1 times another x plus 1, and then above the x-axis. If you remember your, the way, like the Fibonacci, the Pascal's triangle, and you know how to quick expand that, you might know the trick for that. If not, you're just going to have to do it by hand, but it works out to be x cubed plus 3x squared plus 3x plus 1. Okay, otherwise you'll just expand that by hand. Then you'll take the antiderivative of each piece and raise the power on each piece. So it doesn't work to raise the power on the whole quantity. You have to do it piece by piece. So this would become x to the 4th as its new power divided by the number 4. Then it would become 3x to the 3rd divided by its new power. It would become 3x to the 2nd divided by 2. It would become x with a plus c constant at the end, going from 0 to 2. You can simplify, the only thing you could simplify would be the 3's on the cubic term. Then you'll plug in your upper bound. So this would be 2 to the 4th divided by 4 plus 2 cubed plus 3 times 2 squared over 2 plus 2 plus c. So I'm just substituting in the upper bound for all the x terms. Then it should become clear how using 0 is really was a great idea, because when you substitute 0 for all of these terms, they all are 0, and the only thing left is c. Because 0 to the 4th, 0 to the 3rd, 0 to the 2nd, and 0. So that's saving you a bunch of work. And then the c's will cancel out. So you're going to end up with 16 over 4 plus 8 plus 12 over 2 plus 2. So that'll be 4 plus 8 plus 6 plus 2, which works out to be 20. And this had the exact answer area of 20. Okay, I have one more for you. So the last one we're going to look at today is the integral that's going from the bounds of 1 to 3. And the function is 2 plus the cube root of x divided by the cube root of x, and that whole quantity dx. And you might just look at that and get defeated right away. Oh, look at those cube roots, and that's terrible. Okay, it's not so bad if you simplify it into common denominators. So always take a look at the algebra. Can you FOIL? Can you reduce? What can you do to simplify that before you work on antiderivatives? So if you take that into common denominators, so 2 divided by the cube root of x plus the cube root of x divided by its own common denominator, that's going to simplify this quite a bit before you do any calculus. So algebra should always come before calculus. If you can do algebra, do it and simplify. Now 2 divided by the cube root of x doesn't reduce, but it can be rewritten. And when you're getting ready to do antiderivatives, you should always write that as 2 times x to the negative 1/3. So negative to represent that it's in the denominator, and 1/3 to represent that it was a cube root. The other one simplifies to the number 1. And so each of those has an antiderivative now by following the antiderivative rules. So 2x to the 1/3 will become 2x, and what will that new power be? If we're raising it by the number by 1 full unit, it'll be 2/3 now. Okay, when you raise it up by 1, which also means I have to divide by the fraction 2/3. And don't worry, that will still simplify. Plus, the antiderivative of 1 is x, plus the value of c, going from 1 to 3. Dividing by 2/3 is always awkward, and so I would encourage you not to divide by 2/3, but rather to multiply by the reciprocal, which is 3 over 2, which again will reduce for you and help you make an easier equation. So we end up with 3x to the 2/3. Now x to the 2/3 is the same, is still a cube root, but it's a cube root of x squared, plus x plus c, going from 1 to 3. So we substitute, we'll have 3 times the cube root of 3 squared, plus 3 plus c, minus 3 times the cube root of 1 squared, plus 1 plus c. And we distribute our negative. So we end up with 3 times the cube root of 9 plus 3 plus c minus 3 times the cube root of 1, which is 1, minus 1 minus c. So not only do the c's cancel out this time, but also the 3's do. So I'm left with 3 times the cube root of 9 minus 1, which is the value of the exact area between this function and the x-axis.